Again, so I just want to make sure that we understand what we're going to talk about. So basically, there's a bunch of things here I covered because I thought there's too much information here. So hopefully we'll be clear everything out. But I just want you to pay attention to the first word is basically two words. So that means this is not actually computer work. So we are heading towards whatever under towards exactly. So we're trying to make this work, and I'm just presenting the result that we have. It's a work in progress. It's a very interesting approach. I really, really like this idea and want to hear your comments and thoughts about it. So what we're going after is distributed energy resources. So distributed energy resources is basically typical energy resources, but which are much smaller and connected to a distribution grid. And we are particularly interested in residential distributed energy resources. So I am just using rooftop solar as and energy storage as a batteries as example. But as we've been discussing, I know EVs are becoming a good candidate for this distributed energy resources at a residential scale. And the project that I'm going after is monitoring these distributed energy resources. So why do we want to monitor these distributed energy resources at a residential scale? Because they're growing really fast. Okay, and these are it's well known that these distributed energy resources like rooftop solar, they're intermittent in nature. Knowing how much solar you have, it's very important to manage the power bank. So this is actually the goal that we're going after. But what is the status right now we have? So right now, what we have is basically the resources that we want to monitor. They're sitting behind the energy meter. So when they're sitting behind the energy meter, the utility that manages the power grid, they really don't get to see the energy generation of the solar panels, or if you have a battery, what is the generation of the battery? What they see is basically the consumption of the house minus whatever you get from the solar. So that means what the utility sees is the net load. And this is actually problematic. Okay, because the household load, it also becomes unknown when you add solar, because right now the main meter is only reading solar household load minus the solar. So even when you want to do load prediction of the behavior of the residential typical loads, that also becomes problematic. Okay? So now people have tried to solve this, but they have some limitations. So let's see what are the fundamental ways actually people try to solve this. People try to use the data that they already have and try to guess or try to infer from that data. They want to break down what is the load of the house itself, also what is the solar generation. Okay? And typically, a good way to do it is do some estimation of the load behavior, which are more predictable, more repeated. They have a repeating behavior, and add things like solar radiation to estimate the solar. Okay. Now, the problem with this approach is these really, they do rely on the historic data plus the predictable behavior. Now, this is good for regular power grid management. It's perfectly fine. That is actually why people have been working on it, and that they're actually using it to some extent. But the problem is sometimes when the grid has a problem, like a fault, then they do not behave regularly. And that is when the prediction is actually more important. And that is exactly when the system fails. Another problem that we're seeing right now is if you have batteries in those distributed energy resources in the residence, now they add additional variability. So that means you can no longer correlate the solar irradiation with the generation of the solar panel, because your solar panels actually sometimes feeding the batteries. So you cannot really do this anymore. So this is one way. So you are using the existing data that you get from the energy meter to figure out what is happening in these distributed energy resources. The other approach is the opposite way, is directly try to get the data from the inverters itself that comes with your photovoltaic or solar panels. Because these inverters come with smart inverters. So they do have this data collection, and they do report back to their own manufacturers. But the problem is, again, manufacturers, there are different manufacturers. They have their own way of collecting data. And this now, if you want to use that data, it becomes another problem that you now have to buy the data from the manufacturers. Also, they're from different sources. There's actually another line of work who are trying to kind of like filter out bad data or problematic data from this kind of source. So this is also problematic. And another important issue with this approach is it must be intrusive. So that means if you want to know the solar generation, you have to have access to the inverters in the house. Okay. So, but it is inside the customer house, the residence. So we do not necessarily want that. So this is where our solution comes in. So what we want to do is we want to measure the voltage outside the meter. So basically on the utility side, and from this voltage measurement, we want to know the power generation of the inverters. Okay. So again, this is non-intrusive because we are measuring data from outside the house. And this is actually direct monitoring. We're going to show why you call direct monitoring is that I'll discuss that you can actually know exactly how much power is generated from the inverter. You don't have to do any historical data based analysis, or you don't have to rely on any load prediction. How does it work? Okay. This has to do with actually what we have inside the inverter. And it has to do with the power electronic component that you have in all the modern inverters, because modern inverters use electronic switching to generate the AC output, which is a sine wave from the DC input from the PV. Now, the way that they work is, I think the left side is called it's not every inverter has this kind of topology, but this is very like fundamental topology that most inverters use. And then if you are from electrical engineering or you have ever taken a circuit course, you probably know this. It's a bridge design, right? This design will be able to give you bipolar output. So you can do plus and minus. So that is what you can do, but that's not enough because that will be just it's alternating current, but it's not a sine wave. So the way they create sine wave is basically they do a lot of electronic switching, and then instead of getting a real sine wave, what they get is a zigzag sine wave. And that is actually the best they can do. And they use this pulse width modulation technique, where when you want to go up the sine wave, you keep the circuit on for more time, off for less time, and when you're going down, you do the opposite. This is how you get the sine wave. And this is actually illustration. The next figure on the right, this is actually from an inverter, real inverter that we have tested. And if you zoom in, you can see this because that switching happens really, really fast. So now this switching now creates a sine wave which has these ripples or these zigzag patterns. Now, these zigzag patterns actually travel all the way from the inverter everywhere there is a physical connection, all the way to the distribution transformer. And if you connect a voltage probe, which has a sampling rate higher than the frequency of the zigzag, you can capture what's happening to the zigzags. And this is actually what I'm showing on the upper right figure, where the voltage that you can sample, if you take a frequency analysis, you're going to see some frequency component that relates to the operation of the inverter. So basically, if the inverter is stopped, they will go away. Not only that, when the inverter power changes, those component also changes. So basically, we think about that. I'm having 10 watt power output from the inverter. The way what I'm going to see there, it will change when it goes from 10 watt to 10 kilowatt. Okay? That means by collecting the voltage from the outside of the meter, doing this analysis, now we can know what is the power output of that inverter from the outside of the house. So this is actually the basic idea. Okay? So we verified this with some experiments. This is on the left side. I'm showing the setup of the experiment. So basically, you have a solar array emulator which can change how much power you get from the solar PV system. Then we have the inverters, which connects to a distribution panel. And we also have a distribution transformer. And instead of regular load, we put some electronic controllable loads. On the left is the illustration. The right shows the actual setup that we used. And we tested with 3 different inverter models. One is SMS Sunny Boy. Another one is an N-phase inverter. Another one is Schneider from Schneider is called Zentrix inverter. So these three inverters actually have different capacities. And if you know, the N-phase is actually a microinverter. So we wanted to capture both string inverters and microinverters. But anyway, so that's too much detail. But anyway, but the thing is, what we saw was if you collect the voltage after you run this inverter at different power, and then you run a correlation analysis, you see that the voltage actually correlates with the power generation of inverter very, very well. You can see the results is we have nearly 1% RMSE error compared to the capacity of these inverters. So that shows there is a very strong relation between what you see in the voltage outside the meter and what's happening to the inverter. So this is how we can enable behind the meter monitoring of these solar inverters. So what is the advantage? Again, we are now getting direct real time. So instantaneously, we're seeing what's happening. And it's non-intrusive because we're not putting anything inside the customer house. And we are now enabling behind the meter monitoring. And also, interestingly, if you use this approach, you can tell whether an inverter system or a solar system has a battery in it. So for example, if the inverter runs anytime at all, you're going to see the signal. So basically, if you see the inverter running signal in the middle of the night, you know that it has battery in the back. Okay. And but we do have some disadvantage too. So the first disadvantage is that we need at least one sensor for every transformer to collect the information. So this is actually the major disadvantage that we have. Another, I'm not saying it's a disadvantage, but this is something we have is we can only monitor grid-tied system. We cannot monitor off-grid system. So basically, some system that cut themselves off the grid when they want to switch to solar. And there are a bunch of challenges. I have very good answers to those challenges. I'm not going to go over that because we don't have enough time. But I think this is where it gets interesting. I want some feedback from the community is what other applications that we can have.
You want to get feedback.
Okay, yeah. So basically, we can use not just monitoring, we can use inverter behavior modeling, instantaneous or transit behavior modeling. We can actually extend this to monitor EV charging and also things like security items.
Okay, let's take one over.